Hi everybody, Mrs. Pesic here. We're looking at section 4.8, curve fitting with exponential and logarithmic models. Your learning objectives for this lesson, the first one is to model data by using exponential and logarithmic functions, and the second one is to use exponential and logarithmic models to analyze and predict. Alright, so let's start off this example with a little vocabulary. The vocabulary you need for this section is exponential regression and logarithmic regression. Okay, analyzing data values can identify a pattern or repeated relationship between two quantities. So let's take a look at an example. Let's look at this table of values for the exponential function f of x equaling 2 times 3 to the x. Remember, 3 is the base here, and x is the exponent. That makes it an exponential function. So if we plotted a few points here, take x values of -1, 0, 1, 2, and 3, then the f of x values would be 2/3, 2, 6, 18, and 54. If you notice, every time you take the subsequent f of x values, they go up by a factor of 3, meaning you would multiply 2/3 by 3, you would get 2. If you take 2 times 3, you get 6. 6 times 3 is 18. 18 times 3 is 54. That is not the same as what we were doing with first order differences earlier, because first order differences are not all the same. 54 minus 18 is not the same as 18 minus 6, and so on. But what is the same is the ratios. The ratio of each y value and the previous one is constant. So 2 divided by, let me write this down. So for example, 6 divided by 2 is equal to, 6 divided by 2 is equal to 18 divided by 6, which is equal to 54 divided by 18, and so on. There's a constant ratio, and they all are equal to 3. So each value is 3 times the one before it. So the ratio of function values is constant. Alright, so the ratio of function values is constant for equally spaced x values. This data can be fit by an exponential function of this form, f of x equaling a times b to the x. Remember, for linear functions, first degree, the first order differences are constant. For quadratic functions, the second order differences are constant, and so on. But that's not what we're doing here. We're not taking differences. We're not subtracting 2 minus 2/3, 6 minus 2, and so on. We're dividing 2 divided by 2/3, 6 divided by 2, 18 divided by 6, and that's how we're getting the same number each time, by dividing, not subtracting. Previously, we've used finite differences and graphing calculators to find polynomial regressions. Now we're going to use the calculator to find exponential models in the form y equals a times b to the x. Let's take a first example about college applications. Find the exponential model for the data. Use the model to predict when the tuition at University of Texas, Austin will be $6,000. So we're going to do this with our calculator. We're going to enter the data in the calculator, and then we're going to use the calculator to do the regression. So pull up your calculators, please. You're going to show me this when I check this homework in, that you have this entered in your calculator. So for the year 1999 to 2000, let's just put that as year 0. And for 2000 to 2001, let's just make that year 1, and so on. So we need, well, let's first call this something here. Let's call this the year. And then we enter the data. All right, make sure that you push enter after that last piece of data to get that into your table. So now that we have that, what are the next steps? So we entered the data in a list and spreadsheet page. That was step 1. Step 2 is to plot the data on a data and statistics page. So if we do that, go to a data and statistics page, and here we see the data, but it's not organized at all. Click down here for year. Click over here for the tuition. Alright, so there's our data. We want to get an exponential function that's going through this, so we can go to Menu, Analyze, Regression, and we want this one, option 8, for show exponential. So here's our exponential curve. It looks almost linear at this point, but if you look carefully, it is slightly curving. And we have the equation as y equals 3,235.6 times 1.07 to the x. All right, and so what we want to do then is answer the question. And to answer the question, when will the tuition be $6,000? Well, now that we found it, we're going to graph the regression equation and use the table to answer the question. You may want to go to a calculator page. Remember, we push the menu, again, menu, statistics, stat calculations, and I want the exponential regression, which is right here. So I'm going to click that. See where it says exponential regression up here? It's asking for the X list, which in our case is year, and it's asking for Y list, which is tuition. And notice it's going to save it to F1. That's the important thing. That's what we're doing this for. And we say OK. And there's our equation. There's the 3,235. There's the base 1.07 and so on. And it's giving you an R-squared value that says it's a pretty good fit. And so we're going to now graph it. So we go to Control, Doc, Add a Graphs page. And see how it's saying F2? Well, the graph is stored in F1. So just do a little up click. There's F1. Push Enter. And, oh, no graph. So what we need to do is find the graph. If I go to Menu, Window Zoom, and I go to Window Settings, I know that this was for 0 to, we can say 10, and then minimum, we can say 0 for the tuition, up to, it was at least up to 4,188, so let's make it up to 7,000. Right, so there's our graph, and now if we want to find out when is it reaching 6,000, because that was the question. Right? The question says, use the model to predict when the tuition will be $6,000. So what we can do is we can go to Menu, Trace, Graph Trace, and then just type in, is it going to be year 7? No, it's 5, still 5,000. Year 8, that's 5,500. Year 9, that's pretty good. That's almost 6. We're about like 9.1. Yeah, right around 9.1 would be our answer. So that would be the school year of 2008 to 2009 would be our answer for this problem. All right, so here's your first and only notes must do from this. This is the one you're going to do on your own. Use exponential regression to find a function that models this data, and when will the number of bacteria reach 2,000. So we have the time here in minutes. So at time t equals 0, there were 200 bacteria. 1 minute later, there were 248 bacteria. 2 minutes later, 312, and so on. So we want to know when is the bacteria level going to reach 2,000. All right, so you're going to enter the data in a list and spreadsheet page, plot the data on a data and statistics page, find the exponential regression, and then graph the regression and use the table to answer the question. Again, if you want to get all the way up to 2,000, that's hard to do on your data and statistics page, so you might want to, again, go to a calculator page, and then go to Menu, Statistics, and then Stat Calculations, and then to Exponential Regression. Once you get that equation all set up, then you can go to a Graphs page and have fun adjusting your graph so you can answer the question. Or when you're done with this notes must do, go ahead and go on to the rest of this video. Okay, so many natural phenomena can be modeled by natural log functions. You can use a logarithmic regression to find a function. So this time we're going to be using logarithmic regression, not exponential regression. So helpful hint, most calculators that perform logarithmic regression will use ln, right? ln instead of log, all right? Remember, ln is log to the base e. All right, so let's take a population application example. Do you know that there's about 7 billion, 7 billion, maybe 8 billion people on the planet? Well, it's growing at an exponential rate. And if we look at it the other way, where we take the population and the year, we can say, well, at what year is the population going to be, 9 billion, for example. And then you're going to enter the data in a list and spreadsheet page and so on. So let's do that. Go to a calculator. I'm actually I did Control up click because I want to add a new problem to this same document I'm on. You might want to do the same. Control up click, then you push menu and you say insert a problem. Notice I'm now on problem 2, and it says press menu, which I will do, and I'm going to choose list and spreadsheet. At this point, go ahead and enter your data. We're going to enter population here, and we're going to enter year here. Okay, once you have all of the data entered and you've pushed enter after that last data, then we can go to Control Doc. All right, we want to enter a data and statistics page, and so we're going to go population, and over here we're going to be going to year. Notice, doesn't that look just like a nice logarithmic function here? So let's get the equation for that by doing menu, analyze, regression, and we want show logarithmic. And there's our equation, y equals 1,824 plus 106.5 times ln of x. And it's a pretty good fit for the data there. So let's get that entered onto a graphs page. But to do that, we have to go to add a calculator page first. Remember, it's menu, statistics, stat calculations, and we want logarithmic, not logistics, but logarithmic regression, which is letter B. And my X list is population, my Y list is year, and it's going to be saved in F1 because remember I added a new problem to this document. And there's my equation. 1,824 is my A plus 106.5 roughly is my B times ln of x. Let's graph this. Control Doc, graphs, add a graphs page, and I want to go, it's F2, but I want F1. Up click, push enter, and now to see this, we could try to do menu zoom fit. Let's see if that works out for us. There's our graph, and we are wondering, the question for this was, when will the global population exceed 9 billion people? So when will that global population exceed 9 billion people? Well, let's do this a little bit differently. This graph right now is only going up to 2,000. Let's get it to go up a little bit higher. So if I go menu, window zoom, and I go to window settings, and I really just want 0 for my minimum, maximum. Let's make this 10, and let's make this go up to 2050. All right, so there's my graph, and at this point I could, I'm just going to drag it down a little bit. You could do the same. Trace, graph trace, and let's just type in 9. When is it going to be 9 billion people? Well, it looks like 2.06 e plus 3, which means our answer is the year 2060. So our answer here will be in the year 2060. We will have over 9 billion people on the planet. All right, that ends our lesson. I hope you took good notes, and we'll see you next time.